Welcome to the Cosmic Pie Podcast, Episode 11, Season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota. Just to let you know that we do have a chat feature that's running, so if you feel like you'd like to send us a comment, hopefully good comments.
Hopefully.
But we will take questions about anything related to what we're talking about or astronomy or science in general.
Right.
If you ask me what to invest in the stock market, forget that. If I knew, I'd be rich already myself, and I wouldn't have to do this podcast.
There you go.
No, I'd still do it anyways. We have so much fun doing this podcast. The other thing is, of course, is we always give a disclaimer just to legally protect our behinds, our backsides.
Well, not just ours, the university and everybody else's as well.
Well, I'm thinking about ourselves first.
Yeah.
Who can afford the best lawyers?
I can't.
I can't. So
I don't know that I can afford those third-rank lawyers.
Those free ones, right?
Yeah. Pro bono, maybe?
Yeah. You like to give the disclaimer?
Oh,
today,
sure,
Robert?
yeah. The opinions and all that expressed are those of myself and Wayne. They are not those of the university or any part of that system or the state of North Dakota or anybody else.
Yeah, it's just us. We're responsible for not everything. There are lots of stuff going around in the world today that I have no responsibility for at all. There's many other people you can blame. Don't blame Robert and I.
Yeah.
We try to bring you good news.
We try.
If you're feeling blue, listen to us.
There you go.
We'll do what we can to
listen to us.
enlighten your day and make you put a smile on your face, at least for an hour.
Right.
You can watch us make a fool of ourselves and laugh over that if you like.
Oh, I hope we're not doing too much of the making fools of ourselves, but...
Now, if you have
There's
something
always a
against YouTube and you'd rather watch us on some other platform, we do have our episodes uploaded the very next day. It takes YouTube, well, I timed it last week. It took YouTube about 12 and a half hours to process our stream and make it so that I could download it and then do alterations to it, like upload it to Spotify, for example.
Cool.
So we are on Spotify, so if you rather go there and see us, that's great. That's okay with us.
Just watch us.
Just watch us. And of course, as we always say near the end, don't forget to give us a thumbs up on all this stuff. Only a small fraction of people that watch actually give a thumbs up.
Yeah.
And that's true with every podcast. It's not just ours.
It's not just ours. If you like it, give a thumbs up. Come on.
Yeah, and also subscribe, because that one, and ring that bell, they say, and all those fun things. And whatever.
Get the notifications of when we're on.
Just come here every Tuesday at 5 Central, and there's a good chance we'll be here.
Good chance.
Now, one of the things we want to start with today is to look at what happened on Saturday morning, our time. And what happened was there was a
partial solar eclipse visible in most of Europe.
It was, visible, and you can see the Stonehenge, so obviously England. So most of Europe and the eastern part of North America and Canada, United States, wherever the weather cooperated. In fact, the image you see there on the right looks like two devil horns coming up, right?
Right.
That was actually taken from Maine.
Oh.
That image.
So that's why it's on the horizon where it looks like the horns. Because
it's at sunrise.
It's right at sunrise.
And it's beautiful. So you have like the clouds in the foreground, and then they got the sun that's partially eclipsed sun coming up. So, and it's red because it's really low.
Yeah.
And then why is it red why is the sun red sometimes? Robert, when it's low to the horizon?
Because the sky is blue because it's scattering bluer light, which means that leaves red as the color. So the more atmosphere you have to go through, the more blue is getting scattered and the more red things are going to be seen as. Then there's also the dust and smoke and cloud problems. So
then you could ask the question, well, if you go to so you're saying, and let me quiz you on this. I'm setting you up.
You're setting me up. All right.
It's the shorter wavelength optical light that gets scattered more so than the longer wavelength optical light. True?
True.
Then why isn't the sky violet?
Well, actually, I don't know, but I would have to hazard a guess here that it's because ozone and other chemicals higher up in the atmosphere absorb the violet and ultraviolet.
It's actually partly due to the fact that the human eye is actually not that sensitive to violet wavelengths.
Yeah, I knew that. So I knew for a fact to quantify it, that your eye is for a blue or violet light to be seen as as bright as a green or yellow light, it has to be 500 times brighter.
So the eye is actually more sensitive to blue photons than the violet photons.
Yes.
So that's what comes through in terms of our appearance.
So it's our eye problem.
Yeah. And well, not a problem, but it's just the property or characteristics of the eye. Did you want to say anything about yourself in terms of what you can see at short wavelength?
I can say that because I have confirmed it with some experimenting around yesterday. I can actually see a little bit into the UV side of the spectrum.
Oh, you did some recent experiments
Yeah,
on this?
we had some spectroscopes set up for science fair kids that came to the university.
Right.
And one of the tubes, the emission tubes we set up was mercury. And I could indeed, again, like always, I never see it well enough that I can measure the wavelength specifically. But especially if I move around, I can definitely tell there's something there.
So you see a very faint line in the
UV.
near ultraviolet.
Near ultraviolet. That's the qualifier. It's the near ultraviolet.
So just shorter than violet, essentially.
Yeah. And similarly, though, not superhuman, I don't see a lot of the reds that y'all see. So my visual spectrum is just shifted over to the blue end.
Interesting, because that must be a function of, for example, the retina, the sensitivity of the cells on the retina, rather than a lens or the cornea or any other part of the eye that's in front, the aqueous humor, whatever they call it.
Aqueous humor, yeah.
And so it's not a function of any of that material. It must be the retina surface itself then.
Right. I mean,
interesting.
With one of the people helping us with getting the science fair groups through, when this subject came up, I mentioned the fact that I see concrete as being blue. It's tinted blue to me.
Oh, you do?
Yeah. So it's tinted blue.
So it's not white.
Not white or gray or brown.
Or some grayish or whatever.
It's blue.
Well, that begs the question when people ask about the color stuff. You know, we see our own personal color.
Yes.
Because you could say, okay, that looks blue, that looks green, which is very important. Like if you come near an intersection for traffic lights, officer, it was green. I swear,
it was green.
Well, to most of us, it's red. Here's your ticket.
Yeah.
Because the laws are based on most of us. You know,
most of us.
Right. So yeah, it's not like that. It's just that you see a slightly different shade.
Right.
Of a color like green and red and so on.
Yeah. And where it came up originally that I started catching on to this is I got some glasses that were made for looking at computer screens. So they had a faint yellowish tint to absorb the blue light. And I was outside with those on and talking to my wife, and I was like, man, I love these glasses, but I hate them in a way because the colors are wrong. And this discussion came up with her that, you know, concrete wasn't blue like it was supposed to. And she was like, concrete is never blue.
Unless you mix it wrong.
Unless you mix it wrong. Yeah, or right. I mean, there are people who like to color it blue.
Well, that's true. It depends, right? So that's interesting because you can think of like bumblebees that need to pollinate flowers. Their eyes are sensitive to the ultraviolet because flowers glow really brightly at ultraviolet wavelengths in terms of the reflection of that light. So you must be part bumblebee or something.
Could be. It got some bumblebee DNA mixed in or something like that.
That's the bee and Robert.
Our ospreys, because ospreys are one of the shortest lived types of raptors, and it's because they see UV, because under UV light, rodent urine fluoresces.
Interesting. Oh, so it's a trail for them to follow.
So it's a trail for them to follow.
Right. You know, that reminds me of that story from Apollo 13 when Jim Lovell talked about, and it was in the Apollo 13 movie by Ron Howard, the director of that. So he brings up a story, and it was Tom Hanks is the actor that was playing Jim Lovell in that movie.
Right.
And Jim Lovell has repeated this story in his book as well as other times when he's talking to people, so it's a true story. So he talks about the fact long before he became an astronaut, when he was overseas fighting, that he was flying a mission and he was being led by the receiving of signals from a taxi cab in Japan or something like that. And so he was going away from the carrier, and it was at night. Right?
Okay.
And so it's difficult. And so he was going the wrong way, essentially got lost. And at the time, I guess the lights that illuminate your display in the cockpit had gone out, a short.
Oh,
And because of that, he was able to look down at the ocean surface and see that stuff churned up in the water gives off the fluorescence,
The bacteria,
algae and
yeah.
stuff. And that big was long strip due to the aircraft carrier turning up the water. So he just followed that.
so he
and
just
went right
followed
to
the
the aircraft
bioluminescent
carrier.
trail.
Yeah, it's the same kind of thing when you think about it, right?
That it is.
It's
Yeah.
an interesting, story.
I want to see one of those lakes or the ocean when it's doing that.
I've seen
That's
that
one of the
before.
things I
I've
have
seen
not
that
seen it.
growing up on the Atlantic Ocean. I remember that there was occasion, it was extremely rare. Maybe it happened twice
Okay.
in the Atlantic Ocean. I could see that as a younger person growing up,
Right.
that the condition was right to see that effect. It's like I said, it's very rare.
Cool.
So
I'll have to look for it
kind of cool
sometime.
thing. Now, how many people do you know? Let's say percent-wise, do you have an idea who are sensitive a little bit to the ultraviolet like yourself? Do you ever look that up?
I have not looked it up, but I have some some
Empirical?
anecdotal
Okay.
data because at a convention I go to called DragonCon, the track that I volunteer, the programming that I volunteer for, we have had somebody bring out solar telescopes, and that included a calcium K-line telescope. And what I found is that about half the people look through it and see nothing. About half look through and see a purple blob. But there's a few of us who look through, I mean, we're talking less than 1%, that can look through it and see details.
Oh, wow.
And the reason that's important is because the calcium K-line is about 5 nanometers wavelength into the ultraviolet.
So you're talking about the H and K lines?
Yes,
Yeah, they're just short of the 4,000 angstrom line.
right.
So can you see two lines rather than a blob? Is that what you're trying to say?
I can see actually the super granulation and all the other
I
features.
see. On the surface of the sun.
Yeah.
Okay, cool.
So
the convection
and,
pattern.
right, and most, like I said, there's only about 1% of us that can see that. I would say.
Nice.
So I have some experience with how many of us can tweak that little bit extra. So.
See, Robert, you're special.
Yeah, special ed maybe.
Now, the real cool.
I shouldn't say that. I'm sorry, folks.
Getting back to the slide to get Robert out of trouble here.
Yeah.
The real cool thing I like is the one on the left where you see somebody standing by Stonehenge and they put up their eclipse glasses to the sun, then take an image. Mm-hmm. I think that looks really cool.
It does. I got to admit, I wish we could see the sun through it as more than just a dot. But
There's another image that's out there taken by the same person where you can see, different parts of the eclipse.
oh, okay,
And then
cool.
they put it all together as a composite photo with Stonehenge in the foreground.
Okay.
So that looks really nice too.
Yeah.
So I choose this one. I kind of haven't seen this one before. The setup is kind of unique. And of course, where it is makes it, Stonehenge was initially put together like 5,000 years ago.
Right.
And how many human beings were around Stonehenge watching different solar eclipses over the years?
Ooh, that's a good
wondering
point. Yeah.
the mystic things that's going on with that, right?
Right.
So it's kind of cool that the difference there.
Yeah. All right.
Now today, and we normally what we do is go through a bunch of news items that are out there, but today we decided to do something different.
Today we're going to do kind of a picture gallery.
Yeah, so James Webb Space Telescope, which is an infrared telescope, it was launched back on Christmas Day 2021, and we had to wait just a few months for it to get on station and to do all the initial engineering testing until it started to open up for business, if you like.
Right.
And so over the last several years, there's been a lot of images taken of various types of objects in space, of course. And we thought we'd run through this little photo album of some of the different images that James Webb has taken over the last couple of years, and kind of talk about them in detail to get some idea of what's involved here.
Yeah. I do want to ask something because what's the lifetime of James Webb as far as the coolant? Because that's a limiter for how long it can run.
Actually, there's no coolant for the mirror.
Oh.
No, it's passively they're passively cooled with the sunshades protecting it.
Okay.
Because of the multi-layered sunshades.
Right.
That brings the mirror down essentially to the temperature of outer space in the shade. Which is a very, very low level. There's no active cooling. What's the limiting lifetime factor involved is actually the thruster material.
The thruster propellant.
Yeah.
Okay.
And when the nominal lifetime when it was first being launched is 5 year mission.
So next year.
But they wanted to optimize the use of the propellant as much as possible.
Okay.
And when they got it to its position, Lagrangian 2, the L2 position, they said that they have used the propellant so sparingly, they expect a nominal mission of now 10 years.
Okay. That's cool. All right.
So they doubled the mission lifetime.
Yeah.
Which is, now, you can be a little skeptical on that point and say, well, the engineers kind of knew they could do that, but they didn't really tell anybody or make a big deal out of it, because now you can go to the politicians and say, look what we did. We took the taxpayers' money and we treat it like our own, and we extended the mission. We doubled the time of the mission.
Right.
So now it only costs half as much per year.
Right.
So instead of 5
So there
years,
was a little of that going on.
I don't know if there is. I'm just
Okay.
playing the skeptic today, okay?
Fair.
So then when you go back to the politicians, if you never went back, then yeah, you'd say they wouldn't do that. But now you can go back to the politicians and say, hey, we're also like to now this new project, now that James Webb is done, would you please fund this thing?
Right.
And they'll look at your track record and say, you did such a great job.
I do know that that's always...
I'm sure something like that happens. It must, right? It's human nature to do that kind of stuff.
Right.
So anyways, who knows? But the nominal mission is expected to be 10 years. We're only a couple of years or so into it. So we still have a long ways to go.
Okay. So about this image.
Now, this image is an Einstein ring, as you can see here. Do you remember about Einstein? Why do we call them Einstein rings? What's that all about? Just sort of roughly? Like the lay
Roughly,
person
if I'm,
can understand?
it's an effect of general relativity and the bending, the curving of the local space-time around a really massive object like a foreground galaxy, and it can focus light, but it does so by, it's a spherical distortion, so it's going to smear it out around that sphere, is it not? Is it that?
Think like a lens.
Yeah.
Now, when you play with lenses and optics and doing laboratory experiments and so on. So think of distorted type of lenses where you can make weird features, like a fun house at a state fair or something like that.
Okay.
So then you can make, or looking through pieces of glass that weren't really designed to be a lens, and you get this weird effects happening. These, right?
Oh, so that's what's going on, because yes, you can get that ring effect around the edge of a lens.
Yeah, and the joke.
Yeah.
Yeah, and the joke I always use is like the bottom of a champagne glass.
Right.
Tip it up, drink it first, don't waste it, and tip it up, and then look at the lights, let's say in the ceiling, as you move the bottom of the glass across the light source, and you'll see that
mirrors a ring around it.
You'll see that ring
So that's
effect.
what's going on.
Yeah,
Okay.
and then take that symmetry, which is the base of the glass. Extra Bulla is here.
Yeah.
Hi, Extra Bulla. We're glad you made it. We miss you.
Yeah.
So take that, and I'm serious. It's not an April Fool's joke. Okay. So you take that roundness, that symmetry of the bottom of the glass, and if you distorted that, let's say make it like a weird diamond-like shape, then you get these kind of weird features that you would see, right? These lensing, these images that you would get.
So is that what's going on here? All that red and white is
So
an
remember,
Einstein ring?
these are all images taken in the infrared.
Mm-hmm.
So it's nothing you could see with your eye. So NASA color codes the things
Okay.
so that you can get this nice, beautiful appearance. So the colors you see here are not real.
Right.
So you just got to always
You
remember
would
that.
not see this at all.
Yeah, you wouldn't see that at all because in the infrared. What you see, so they illustrate the light coming from the background galaxy, not the foreground galaxy, is blue in color. And that's to show that that's coming from a star-forming spiral-like galaxy.
Oh yeah, because now I can see the same points in multiple places around the. Okay.
Yeah, and you can see the blobs in that light. So
Yeah.
those are star formation regions in that background galaxy. And the galaxy that's in the front is the one that's in the center. That's an elliptical type galaxy.
Mm-hmm.
That's lensing the light from the background galaxy. So just like looking at a light through the bottom of a champagne glass, things have to be aligned up the
Just
right
right.
way in order to see that ring-like effect. If you have it off to one side, you'll see a partial ring. And by extension, any mass will do this, technically. So even a ball bearing curves the space-time around its vicinity.
Right.
And under the right sensitivity, if you could have that, in right instrumentation, you could measure the distortion of light when it passed near the surface of that ball bearing, because it's passing through space that's not absolutely flat.
Right.
It's curved.
And my response on that, though, not to seem cynical or anything like that, is this is about like the student one time that told me the lens that we'd given them to find the focal length using various methods. They told me that lens they were given had a focal length of 8,000 meters. Okay, folks, that's not a lens. That's a piece of glass.
Infinity.
Okay, that's a flat piece of glass. So the ball bearing would curve space-time so little that essentially it's a piece of glass.
But we have the technology. We can be able to detect.
I will agree with that. We could detect it. We wouldn't be able to
in space.
See
It's hard to get anything out of that.
Right.
But just to be technical, anything would produce that.
Absolutely. Yeah.
And you could think of even planets going around extrasolar planets going around other stars would do the same.
Right.
It would distort the light of the host star when they're in front of it. Mm-hmm. And as they move across, right,
it would change.
We'd be able to detect
kind of
that.
Yeah.
And if you had an interferometer, like Nick was talking about with the char array, I'm sure you'd be able to measure that effect.
Ooh, yeah. Okay. Things to try.
Things to try. Okay. On to our next image in the photo album. So this is also JWST images, they all are. In particular, this is the combination of the near cam and the MIRA, so the mid-infrared imager as well, laid together.
So this is near infrared and mid-infrared.
Yeah. And this is a barred spiral galaxy, NGC 2283. And you can see, and when you look towards the center, is there really a bar there? Well, there's sort of a bar. It's almost horizontal, but not quite in this projection.
Yeah, I was about to say, I don't really see the bar in this.
Yeah, it's amazing, right? That this is you could look at what a bar looks like in the center of a galaxy, and then look at it in other wavelengths, and it fades away. And and in other wavelengths, it becomes more prominent. So the prominent feature of a bar actually depends on the wavelength that you're looking at.
Right. That was what I was going to comment on. I would actually now like to see a visible light image
on top
of this NGC 2283, because the bar may be visible in the visible wavelengths, but I'm not going to buy it in the infrared.
And what you're seeing in the infrared, of course, is mainly dust.
Is dust.
So you're seeing the outline of dust. That's why you see the spiral features.
Especially with MIRI.
Yeah.
The mid-infrared, because that's essentially long wavelength infrared, and it's where dust is being heated.
And the typical sort of observing effect that you notice is that the spiral arms begin at the end of the bar.
Right.
So you have a linear-like feature that runs through the center. That's what we mean by a bar. It's not where you go to drink.
Yeah.
Watch football. And and at the end of the bar is where the spiral arms begin. But look at the spiral arms where they start near the center. They almost start at exactly the center.
Yeah.
So do spiral arms really begin at the end of the bar?
Right.
So
do they really? Again, this calls into question: does the bar really exist?
Well, it exists in other wavelengths, like optical wavelengths. But in the infrared, that the dust does not outline that bar well. You can definitely say that.
And I will also throw out a greeting. We got Brian Acosta that showed up. He's been here a few times too. So anyway.
And the other thing to notice here is there are several stars, foreground stars from the Milky Way, that's in the same line of sight. Those really bright objects that have those large diffraction spikes on them.
Yep.
There's one sort of in the bottom right, one up almost directly above it, also on the right, one over to the left, and a really faint one in the upper left.
I was about to say, there's a lot of faint ones, because if you see those spikes, that's a foreground.
Yeah.
That's a star in our galaxy.
Yeah. Yeah, they're saturated in this image.
Yeah, if it's just a bright dot, chances are it's in the background. It's somewhere else.
Yeah, exactly.
All right.
So
shall I look at the next picture?
On to the next one. So we're stepping out now. That previous galaxy was about 45 million light years away. So just think of it. The light that was recorded by the telescope left that galaxy 45 million years ago.
Yeah, and 76 for this one. Yeah.
76 for this one, which means that when the light left this galaxy and made this image, then
Dinosaurs,
dinosaurs were still roaming around
Yep.
doing their thing.
Now, I'm looking at this one and thinking this is a interacting or disrupted galaxy of some sort.
Well, first of all, there's a couple things you'll notice here on this one.
Okay.
Is number one, that it has a fairly bright central region.
Mm-hmm. Because it's got the spikes, so that's bright.
So it's really bright. So it may be an active galaxy. I didn't see anything in the description of it. I never looked in detail to see if it's on the list of being an active galaxy. And by the way, an active galaxy is a galaxy that has a really bright central nucleus area. And that's due to the combination of two things. Number one, the presence of a supermassive black hole.
Mm-hmm.
And it turns out almost every normal galaxy that we see out there has a supermassive black hole at its center, including our own Milky Way.
Yep.
In fact, the Event Horizon Telescope back in 2018, I believe, released the image for the first time ever taken.
That was M82, wasn't it?
It was M87.
87.
And then the second one they released was the Milky Way itself, our own
Yeah.
galaxy. And the black hole, depending on what reference you use, I've seen numbers anywhere recently, there's not old numbers, 4 million times the mass of our sun up to like 4.3 million times. So it's roughly 4 million times the mass of our sun, that type, the black hole that's at the center of our own galaxy. So if you find a lantern up in your attic tonight and you rub it and a genie pops out, don't ask to go to the center of our galaxy as a fun thing to do, because it would suck.
Bad Wayne.
Now, so the active galaxy has a supermassive black hole, but it also has material just outside the black hole, just outside its event horizon, and that's known as an accretion disk. When that material then moves in that accretion disk and is drawn in from outside of that in a larger sort of donut shape torus, as we call it. So Homer Simpson would be happy, right? You draw into that material, it spirals around, and as it spirals around, then it heats up. Think of friction.
It rubs against itself,
and that it'll heat up to a point where the temperature gets so high, and we mean millions of degrees, that it emits lots of X-rays. Well, besides X-rays, it's emitting optical light,
and infrared.
Any dust and stuff in the material gets heated up, so it emits lots of infrared, and that's why this central object looks so bright.
Right.
Probably an active galaxy.
The other reason, because all that material is being drawn in by the black hole, is you also get a lot of shock waves that spur star formation.
Yeah, well, that material gets consumed pretty fast.
Well, if it's too close, but
yeah, so stars really don't have time to form out of that.
Oh, okay.
It's too much of a hostile
Thought
environment.
out of the edges where it
you got to be much further out, right?
Yeah.
And the other thing it can do is actually go the other way. It can truncate or quench star formation.
Well, that's true
because you have radiation coming off the disk,
accretion
disk, then it can push the material out and also heat it up. So
where
then gravity can't collapse it.
Right.
So remember, in star formation, in order to form a star out of a clump of material, you want its density to increase dramatically, but you want it to be extremely cold so that you can collapse it down to the point where you can convert, let's say, hydrogen into helium through thermonuclear fusion before the temperature gets so high and the internal pressure gets so great, it kind of expands itself. It resists being collapsed.
A compressing gas heats up.
Yeah.
An expanding gas cools down. So this is part of what leads to Herbig-Haro objects, if I'm remembering correctly. The fact that they're collapsing, they heat up, they now expand a little bit, and they just keep pulsating.
We can think of variable stars, right?
Right. Variable stars as well. Yeah.
That same mechanism. But this is a cool image. In fact, you can see almost like a ring-like structure on the outside, and that's big ring of dust.
Okay.
So star formation area clearly in that part of the galaxy itself. So the central part has cleared out its central region.
That's why I was thinking it was a disrupted galaxy.
Yeah,
because that's usually what that clear area in the center means.
Where the center region is so bright, right? I wouldn't doubt that this is an active galaxy and it may
have cleared out.
Yeah. But yeah, I'm sure people are still studying this, but it's very interesting for sure.
Oh yeah. So the next one, we've got something in Perseus molecular cloud. Okay.
Yeah, so what do you think's going on in this region of space?
Oh, that's clearly a star forming region.
Exactly. And That's the beauty of infrared. Why would you want to use infrared to look for star-forming sites rather than, let's say, blue light, optical blue light?
Again, because the dust scatters blue light, so you can't see as deeply into the cloud because of that dust and everything. So infrared, being even longer wavelength than red, can penetrate deeper.
I mean, that's the whole thing of trying to understand in nitty-gritty detail the processes of star formation, which means how do you take a lump of material like you see in a molecular cloud like this one and transfer it ultimately into a star like our sun?
Right.
What are all the detailed steps? And that's what a scientist obviously wants to know, is what is the detailed physics involved in all of this? Well, you like to study these little knots that you see here, these little bright areas, and that's not the ones with the diffraction spikes. Those are stars, ordinary stars.
Right.
We're talking about little clumps, little ends, little finger, little protrusions sticking out in some different places, especially near sort of the top center that you see there. Yep. We would like to look down in the heart of those regions to actively watch objects that are ultimately turn into stars, and we call those objects protostars, and if they're further along in their evolution to become a star, we call them pre-main sequence stars.
Right.
The problem, as you alluded to, is they give off light.
Which heats up the gas and
Well,
dust.
they give off light, but the surrounding material is so dense,
Right.
and it's drawn towards that high density region, that any of the optical light, let's say we started with thinking about blue light, any blue light that's being emitted is going to be constantly absorbed and scattered by the surrounding material, which we call interstellar matter. So that light can't get to the outside and then ultimately get to us so we can see it. So what can make it through that material then is the much longer wavelength light, like infrared or even into the submillimeter, into the radio.
Okay.
And so you want to look in these regions then at longer wavelength, which means that, that's why you want to use infrared, for example, to do that.
And I love this because to me, I'm sitting here, I'm seeing it being sculpted, the cloud being sculpted, which means that there's actually some nearby young stars that are putting out a lot of UV light and are eroding the cool cloud that is forming stars.
Well, and some of the stars that you can see there, so objects that have become stars, they could be embedded within that material as far as we know. We don't have any way of knowing the distance to the individual stars from this image that we're seeing here.
Yeah.
Now, this area is relatively close when you compare it to like the Orion Nebula. So this is like 960 light years away. As you see there, the Orion Nebula is depending, because it has a three-dimensional, has a depth.
Has a depth.
So the front surface is probably somewhere a little bit more than 1,200 light years away from us. The middle or back side is probably closer to the order of 1,500. So it's several hundred light years, in depth type of thing. And that's typical of what we call a giant molecular cloud. You're talking about diameters from 30 to up to 500 light years.
Right.
Depending on the one you're looking at.
And that's what I try to point out to people is just the nebulosity we see is because it's so thick. It's hundreds of light years thick. If you were actually in the cloud, while we have techniques that we would know, hey, we're in a cloud, you would not be able to go out at night and see the cloud.
Oh, it's a great place, I understand, to hide from the Romulans, too.
There you go. The Mutara Nebula.
Well, it's similar, like if you're looking at fog in the distance, you don't see all through the whole fog. You just see that front scattering surface, right? That last scattering surface
There you go.
of the fog bank. You don't see what's behind the fog if it's too thick.
Right.
So it's that kind of effect going on here. But it's interesting. If you want to study star formation and understand
These are the
these are
places.
the place. This is a stellar nursery, essentially.
Absolutely.
This is where you want to look.
Pardon. Okay, so the next one.
So the next image, and getting back to lensing again, this is lensing of a quasar, and you can see three sources and even a fourth one down below. So these are images of the same object, right?
And
a quasar is an active galaxy, once again, a supermassive black hole with an accretion disk, and they are the most luminous of all the active galaxies. So they produce a lot of energy per second that radiates from these sources. And this material is passing through a galaxy cluster, and the cluster itself, right, the quasar itself, I should say, is at a distance of about 6 billion light years away.
Wow.
The light coming from this quasar left that quasar before our
the
solar
sun.
system was
Yeah.
even around.
Yeah.
We would have to wait another 1.5 billion years for the Earth, as well as the rest of the stuff in our solar system, include our sun, to form.
Right.
So this light, in other words, has been on its way to us
For a long time.
for 1.5 billion years before us was even here.
So about half the age of the universe.
Yeah, if you think the age of the universe is about 13.8 billion, so this is
Right.
getting close to half the age of the universe.
Right.
You know, it's
wow.
mind-boggling, and when people make that comment a lot, you know, when you talk to people, the general public, you just mentioned about doing outreach, for example.
Right.
And we talk to the people, and they're not into astronomy, but they know a little bit about it from what they hear on the news meters, see on the computer, and all this kind of stuff. And you talk about these large distances, and when you stop and actually think about it, so you scientists kind of do the calculation, you move on. In some sense, it doesn't become a gut feeling of what you're actually looking at. And
Right.
but you try to impress your students to do that, to think about what those numbers actually mean.
Right.
In fact, that's where you find mistakes. You calculate the mass of a mouse, and it's 3 times the mass of our sun. You made a math error somewhere.
8,000 meters for the focal length of a lens.
Yeah. So you look for things like that. Obviously, that's kind of, you get trained to do that.
Right.
And it seems like it's more common sense. But what do the real numbers actually mean? 6 billion light years away. So the light takes 6 billion years to get here.
Right.
It's amazing when you think about it.
I mean, that galaxy probably isn't even there anymore.
Yeah. That quasar could long have used up all of the material, and the active nature of that galaxy has now shut down completely.
Right.
And if the last photon left that quasar now, we'd have to wait 6 billion years before it would reach us if it was heading in our
I
direction.
hope we're around a new star because the
6
sun
billion.
won't be around then.
Well, not even that. The Milky Way won't be around because it will have long since, as far as we know today, merged with the Andromeda galaxy.
Andromeda way.
Yeah. So it'll be a new galaxy. It'll look very much like an elliptical galaxy sitting in, dominating the local group of galaxies that both
Right.
the Milky Way and Andromeda are part of now. So a lot of things are going to change. That's one thing about, things in space. Always changing.
Right.
Always. And along with that is our technology that's always seemed to be improving, and we discovered new things all the time. Imagine us doing a podcast someday, Robert,
Okay.
and it's only based on news items, like new research that came out in our field. Well, if it changed very little, you do a podcast every year or something, and that's it. You can
Right.
cover all the
Right.
bases. But sometimes it feels like we can't even cover everything, and we do a weekly podcast. You'd almost have to do a
We
nightly
can't.
podcast.
That's the thing, and it's not necessarily that things are changing with what we're seeing. It's just what we're able to see, the resolutions, the spectra, the details change.
Yeah, it's
and
a-
suddenly we know more than what we did a year ago.
Yeah, because you could ask, for example, when did astronomy really take off as a science? Well, the time of Galileo.
Right.
And why was that? Was it because Galileo was able to make better pizza than anybody else? No.
No.
It was because of the use of the telescope at that time.
Right.
Even though he didn't invent it per se, he used the telescope to make astronomical observations, published what he saw,
Right.
told people about it, and this began that improved astronomy greatly at the time.
Right.
And then it's the push of technology of building instruments that allow you to see better and better.
As I term it, he's the first one to take a telescope, turn it to the sky, and then write about it.
Yes, exactly. Published his books.
Right. Because as the Mythbusters, I love them. As Adam Savage once said, the difference between science and messing around is writing it down.
Well, it's interesting. We celebrated back in 2008, I guess it was, like the 400 years since
Of
Galileo.
Galileo. Yeah.
And at that time, I remember a story came out where researchers they dug into Galileo's things again, what he left behind. And what they discovered was there was an Englishman who actually made a drawing, a very detailed drawing of the map, one which you could never do with the unaided eye. He definitely had to use a telescope. He got the position of craters and mountains and valleys and so on the moon correct.
Okay.
So there's no way, even if he had slightly better than 20/20 vision, he was not able to see all of the detailed features he put on his drawing. But so he clearly used a telescope. This is before Galileo.
Oh, wow.
And he took that drawing and put it essentially in the desk drawer and closed the drawer and never published it.
Well, there's the problem.
So that just says you don't get credit for anything in science unless you publish.
Right. Absolutely. So get to writing. Ooh, pretty.
Now, this is one of my favorite objects. This is a globular cluster and catalog number NGC 6440. NGC, by the way, just means the New General Catalog. That's what it stands for. This particular cluster of stars, it's in our own Milky Way galaxy. It's 28,000 light years away.
So it's even on our side of the Milky Way.
Well, it's 26,000 to the center.
Right.
So if you say the distance from here to the center is 26,
Okay,
it
so
depends what direction it's in.
Okay.
Yeah, I don't know exactly the location.
Could be above, below
Yeah,
the bulge.
Yeah, so you'd have to go look to
Okay.
see exactly where it is. Chances are that it is,
Yeah.
right? But it's probably closer to us than it is to the center of the Milky Way.
Right.
So what you can see in this image, of course, is the different types of stars that make up this globular cluster. But the one thing that's always interesting is the high density.
Right.
Look how dense the stars are. And this is with a telescope, 6.5 meters in diameter, that's in space. That, number one, is not affected by the blurring effect of Earth's atmosphere, so it has a very sharp view. Number two, when it works at the diffraction limit of the telescope, it's even sharper than the Hubble Space Telescope because it is much larger in terms of its diameter. You know,
Right.
the Hubble is 2.4 meters in diameter. This is about 6.5. So it can see a lot sharper in terms of angular resolution. It can see much, much finer detail on a given object than the Hubble. Now, the other thing is, it operates in the infrared and near infrared and so on, and so that degrades the angular resolution a little bit, but the larger aperture size makes up for that.
Makes up for it. Yeah.
So the interesting thing about it is even in the highly compact, dense region in sort of the upper center, imagine yourself now on a planet that orbits a star in that region of the globular cluster.
Night. What's night?
It would never be night.
It would never be
So
night.
would there be no nocturnal creatures, you know?
Right.
You'd never say, I'm going to sleep when it gets dark. It'd never be dark. We'd have to sleep. I wonder if life that evolved on a planet that orbit a star in the center near the center of a globular cluster if it would be like humans, and let's say the average age of a human, life expectancy is 80 years, would we only live for maybe 40 years because we'd be up all the time? Like
Right.
we'd never sleep.
We burn out quicker.
Yeah, we burn out a lot sooner.
Yeah. I have to wonder what the radiation levels would be like.
That's true. Now, if you had an atmosphere
Yeah.
that had strong ozone layers and stuff, you could protect yourself.
But
And the other thing is, if a creature evolved on a planet like that, it probably has its own protection, like Ninja Turtles.
True.
So you have a shell-like exoskeleton that
Yeah,
would protect
yeah.
you from harsh radiation coming from all of the nearby stars.
yeah.
But yeah, it would be amazing.
It would be
to see
amazing.
that.
I've read some stories about people imagining life in a globular cluster, and one of the things they also point out is that this would be an interstellar faring species if they were intelligent and developed rocketry and so forth, because the nearest star is right there.
Your backyard.
Yeah. So
Interesting.
instead of a hundreds of years jaunt, it's a few tens.
Now, the only bad thing about it in terms of life as we know it is globular clusters are, in our galaxy, are
Old
very old.
stars.
And they're made from relatively metal poor material.
Oh,
So
forgotten about that point.
Yeah, so any planets that do form around these are not going to have the high metals that we would have for the Earth,
Right.
presumably. So if you take away the metals,
They're probably not spacefaring because they don't have the industrial structure.
I wonder. I don't know.
I don't know. I would love the opportunity to find out.
Too bad we couldn't like send a probe there and send back data
Yeah.
fast enough. Like, but obviously that's science.
That's-
That's science fiction.
That's hundreds of thousands of years there.
Well, and the other thing is, how do you get the data back? If it travels at the
Right.
speed of light, it'd be 28,000 years. We're waiting for the first picture of what it would look like.
Right.
Unless you use sci-fi stuff and use quantum entanglement, which nobody, right?
Yeah.
You know, but that, you know, by the way, for those of you who have heard about quantum entanglement and think that's a way to transmit information at greater than the speed of light, it doesn't work.
It doesn't work
The
that way.
information is so distorted you can't get anything useful from it.
Right.
So there's no way, as far as we know today, I always put that caveat on there. As far as we know today, it's no way that we can have faster than light travel through quantum entanglement.
Not useful information.
Not useful information.
Yeah.
So, but what will happen 500 years from now? Will we better understand quantum mechanics that maybe that does violate special relativity? Well, we don't know, of course. I can't say. So I'm not going to, there's no absolute in science in that sense, right?
I mean, I mean, this distance between us is really just an energy barrier. So more what I'd be looking at is tunneling, quantum tunneling.
Right, so you could transport yourself from here to
Right.
there instantly, essentially.
Just have your waveform set it up in such a way that
Now, of course, if you could develop a rocket that travels very close to the speed of light, so you don't violate any known laws of physics,
you would get there.
you would get there in a relatively short period of time, because you just have to accelerate at like 1g, which is what we feel here standing on the surface of the Earth, and keep going until the point where you have to turn around and then go the other way.
Accelerate for 1G.
1G.
Back. Yeah.
And how long would that take, right? It's so a few years. You'd make it in your lifetime.
Right.
And but everybody else back on Earth, there would be more than 28,000 years have elapsed. So
Right.
anyone that you know, of course, is long since gone.
Time dilation, it's a thing.
Yeah, well, we have to worry about that, I guess.
All right.
Yeah.
Yeah. So what about this one? I mean, this one's got a lot of bright foreground stars.
Okay, so the first one was a globular cluster.
Okay.
So it has, upwards to 1 million stars all jam-packed in a volume of space of about 100 light years or so in diameter. Very old type of objects. In some sense, they formed just when our Milky Way was probably forming. This object that you see here is an open cluster.
Our
Now,
sun likely formed in one of
or
these.
an OB association, which is like a
Could
poor
be.
man's open cluster.
Yeah.
Right? So we don't know. The thing about that's a good point, and we should stress that. The majority of stars that when we survey them are not isolated.
Right.
They're either in a binary star system, so there's two stars that orbit around the center of mass, and if they have equal mass, that center of mass, by the way, is exactly between the two. You have a teeter-totter or seesaw effect. Okay.
Right.
And then there are also systems in which there are 3 stars in mutual orbit around each other, or even 4, and we've seen 5, and even evidence of 6.
And the deal there is they have to be hierarchical, though.
Yes, yeah, you could have one star that's really far away orbiting, a bunch of stars that are near the center area, and that would count, of course. But the thing is, our sun is kind of unique in a bit. It's in the minority, statistically, that there is no other companion star to our sun.
Right.
But when you look at stellar nurseries, like the Perseus cloud that we look at and many other areas in our Milky Way and in other nearby galaxies, you find that when stars form, they don't form totally isolated. We expect to have several stars form in the roughly the same volume of space.
Right.
So it's fair to ask the question then, if our sun formed in that type of environment where there were at least a few other stars that formed at the same time, in other words, our sun has brothers and sisters, siblings, where are they?
Where are they?
Now, it's almost like, human beings. If you had a brother that you didn't know about and you were separated as young children, so you don't have any memory of another person being in your family, and then, 40 years goes by and somebody suspects that they're your brother, how can you tell today if that's the case? What's the one surefire way of knowing for sure if somebody is related to you, is your sibling, is your brother?
Oh, that's DNA test.
DNA analysis. In other words, you do detailed examination of your composition.
Right.
So what you can do in this case, when we're talking about the sun, is you look at the sun's composition in detail, which means analyzing its spectrum.
Right.
Look at what it's made up, what are the different types of atoms that's in our sun and so on. And then look around at the spectra of other stars and see if you can find a perfect match to our sun.
Right.
Now, people do that. It's not like it's new. That's been around for decades, right? That's that thought process. And there are people out there actively looking for siblings to our sun. But so far, no joy, as they say. We haven't found a brother or sister to our sun.
And that's because we do know that these open clusters are unstable. They are torn apart by both the interactions between the stars themselves and the Milky Way, the gravitational forces of the overall Milky Way galaxy.
Yeah, so now remember the sun, and we only know this because we can do radionuclide dating of rocks on the Earth, that the Earth is 4.57 billion years old, and therefore we infer that the rest of the solar system, including our sun, probably formed at the same time that the Earth formed. So we'd expect our sun to be about 4.5 billion years old as well.
In fact, I will point out we now have some constraints on how fast planets form, and we know it's not a matter of the sun is 1 billion years older than the planets. We know it's probably less than 100 million years older than the planets. So
in that case, if there were other stars, other brothers and sisters to our sun, at slightly different distances from the center of the Milky Way, but nearby initially, over those 4.5 billion years, the sun has gone around the Milky Way like 18 times.
Right.
So any of those other nearby stars initially would have been spread out in their orbit. So they literally could be on the other side of the Milky Way from us.
Right.
Which is why at this moment in 2025, we haven't found any.
No joy, no joy.
Yeah, no siblings to our sun that we recognize. It doesn't mean that they're not out there.
Yeah. I was going to mention that there have been a few papers where people have said, hey, we found one, but they are later retracted because no, not quite a match.
Yeah. And the other thing about this image is look at the nebulosity.
Yeah. So there's still
cool.
maybe stars forming there.
Well, and we don't know because
mass.
I should have put an image here of the Pleiades, right? That's a classic one. When they did long exposure imaging of the Seven Sisters or the Pleiades, you can see it's a reflection nebula. You have all this interstellar matter in among the stars. And so they said, aha, that's the material from which those stars were formed from.
Nope.
And just like we said about DNA, you do CSI astronomy, you take the detailed compositional measurements of that material, looking at the spectrum, compared to the stars embedded within the material, and they are completely different.
Right.
In astronomy, you'd say their metallicities are different. So what we think is that the Pleiades, as an open cluster, it just happens to be moving through a totally independent cloud of material right now.
Right.
And gave the illusion that it was
embedded.
material from which it formed from.
Could be the same.
And that could be the same as far as we know.
Yeah.
Right?
So here's another neat one.
Yes, so in this one here, this is a star-forming region also, but it's not in the Milky Way. It's in a nearby satellite galaxy to our own. It's a low-mass galaxy, which we call a dwarf galaxy. By the way, there are politically incorrect words that we use in astronomy.
Right.
There are dwarfs and giants. They don't refer to people, and we don't use them to refer to people. They're referred to things that are not alive, like stars. So please don't get upset.
Yeah.
And this is a hangover from like 1800s and early 1900s.
And it's a reference to their size, physical size.
Well, so are when you call a person.
I get
you're talking
it,
about an individual, and it's nasty.
Okay, so we'll go back to these are things that don't have feelings that we need to worry about.
That's it, right? Yeah. So anyway, this star-forming region is in the Large Magellanic Cloud. Now, Large Magellanic Clouds are viewable when you are below the equator, south of the equator. Mm-hmm. In fact, the first time I've ever seen them in my life was when I went on an observing run in Chile. Mm-hmm. And I remember my first trip to Chile to use a telescope. You're on top of the Andes Mountains. It was at the Cerro Tololo Inter-American Observatory. And the Magellanic Clouds are so obvious to see with the unaided eye. They're just beautiful.
Just right
They're
there.
just fantastic. Right? You could see them like that. Anyways, and they get their name, by the way, from Magellan, who circumnavigated the globe, right, in the 1500s, and he reported in his log, says he never made it back on that trip.
He didn't.
So in the log books is reported the cloud-like objects in the sky. Of course, anyone who lived in the southern hemisphere knew they were always there, so humans knew of their existence for depends how far back do you go and still call that person a human. A million
Right.
years, 2 million years, whatever. Whatever that time is, right? It's all number. It's all, those creatures don't care what we call them, right?
Right.
As long as you don't call them late for dinner, they're okay, right?
There you go.
So people that were alive knew about the existence of these, but people in Europe didn't.
Right.
Because at the time, not many people were able to go south of the equator if you lived in like Italy or something, right?
Right.
You have to be on these large exploration and very dangerous type of trips, of course, expeditions to do that, Magellan being one of the most famous ones. And so anyway, so this is a star formation region in the Large Magellanic Cloud. And the other interesting thing about it is that it's near the site where the supernova was observed to go off back in 1987.
1987.
And remember, we had Ian Sheldon on our podcast there a few months back. He was the person that discovered that supernova.
Right.
World famous ever since. It was the closest, brightest supernova in like 400 years.
Right.
Just before the Galileo's use of the telescope.
It was naked eye visible in the southern hemisphere.
Yeah, we weren't able to see it up here for those of us who were alive at the time. So hopefully, that's why I always look at Betelgeuse as like, when is that one going to go, supernova?
Right.
Because then we'll all get to see it. And hopefully it's not 10,000 years from now. Hopefully it's soon. And before I go blind or something, and I want to be able to see it, right?
Right.
That kind of thing.
I agree.
So.
I agree.
Anyway, so this is a nice star formation region. It's 159,000 light years because it is in that small satellite galaxy to our own Milky Way. And why you want to study these kind of things is clearly you want to be able to compare, well, what are stellar nurseries like in our own galaxy? And what are they like in other galaxies? Are there any differences? And if there are differences, why are there differences? So you can go down this whole rabbit hole of looking, of contrasting and comparing these type of regions. So by studying lots of different types of stellar nurseries, you can hopefully piece together all that information to say a lot more about star formation itself.
And the answer is there are differences. They're not major, but there are differences. So
there are. And I think the last slide we'll show is the next one for today. This is an active galaxy.
That's an AGN.
And you can see the brightness of the center. So this sucker has a supermassive black hole in its heart in that accretion disk. So this galaxy is about 220 million light years away.
And there's a foreground galaxy in the lower corner.
Yeah, you can see galaxies are in the background as well as in this image. You can see all kinds of them here. But the brightness of the central region really stands out, as you see from the diffraction spikes. And that weird feature about them spikes is due to the way the telescope was constructed with the separate segmented mirrors that are folded together and the way the light combines. You get these artifacts.
Right.
In fact, if you looked at it with your eye, if you could see that, you wouldn't see that structure.
Right. You just see a bright star.
Yeah, or you used a different telescope to look at it.
And the spikes would be different.
And the spikes will be different or even gone depending on the type of telescope that you're using.
Well, I won't say gone because even with the Schmidt-Cassegrain where the mirror is suspended on a corrector plate, you'd have circular diffraction pattern.
If you think about those offset mirrors,
okay,
the light comes in and there's no secondary mirror in the way, it bounces to the side.
Like a YOLO, yeah.
Yeah, and so you wouldn't get that effect, you see.
Fair.
In fact, if you look at data taken by the Eclipse mission recently, you don't see all those diffraction spikes.
Okay.
So that's a different type of design. Anyways, this is a beautiful example of an active galaxy. And if you want to study black holes, and not just black holes, but these supermassive black holes can be billions
of times
of solar masses. And in fact, the really mysterious thing going on today is that we see evidence for these black holes in galaxies that formed essentially only a few 100 million years after the universe formed.
So
how do you form these supermassive black holes so quickly? That's a puzzle that people are working on even
So come join us and learn how.
Yeah, if you want to get involved in these type of investigations to uncover the secrets of the universe, well, why not come to the University of North Dakota?
Absolutely.
And learn.
It's a nice place. It really is.
It's a beautiful spot. You can come take online classes if you like, or you can come here on campus and take classes, not only in science or in the STEM fields. We have programs that cover all of the bases.
Right. Help us translate it into that writing we mentioned. Come join the English department.
Science communication is a big thing. And
Absolutely.
Having people that know how to communicate and have a little bit of that
see the
science
comms department.
Yeah, that science background is really a great thing. And so we really appreciate all higher learning.
Absolutely.
And be a lifelong learner. That's the way I look at it myself. Now, our next podcast will take place next Tuesday, April the 8th. We always leave you with a quote.
Yeah.
And today, the quote is by Sean O'Keefe. He was a NASA administrator from 2001 to 2004. And what the quote is about is the fact that he was the one that named the JWST, the James Webb Space Telescope.
Okay.
And Webb himself was also a NASA administrator at a very exciting time in the history of NASA, between 1961 and 1968, when the United States was gearing up to land on the moon.
Right.
So that must have been an incredible job and a lot of responsibility.
Yeah.
You know, in that sense, you're scared to death of something. And then, of course, during that time was the Apollo 1 fire and stuff. So, yeah, there are a lot of things that happened in that time period. So the quote is about naming the telescope after James Webb. So here's the quote by Sean O'Keefe. "It is fitting that Hubble's successor be named in honor of James Webb. Thanks to his efforts, we got our first glimpse at the dramatic landscape of outer space. He took our nation on its first voyages of exploration, turning our imagination into reality. Indeed, he laid the foundations at NASA for one of the most successful periods of astronomical discovery."
Nice.
Thank you very much for watching. Don't forget to give us a thumbs up if you can, and please join us next time. Thank you.
Good night, folks.